Hello, and welcome to The Dreaming Scientist, a quiet place in deep space with softly spoken science for your sleepy minds. Tonight we will walk slowly through a big question with small, careful steps. Is time real, or is it an idea we invented to make sense of change? So settle in, dim the lights, and get cozy. But before you do that, take a moment to like the video and subscribe to the channel if you enjoy the videos. Also comment down below where you are watching from. It is always intriguing to know who is watching us from around the world, and thank you so much for being here. Before we can ask whether time is real, we have to untangle what that small word is doing in our heads and in our equations, because it points to two different things that we often mix together. One meaning is time as experience. You feel a present moment, you remember a past, you expect a future, you sense a flow as steady as your breathing, or the pulse in your wrist. The other meaning is time as structure, a number on a clock, a coordinate that lets physics place events and compare them, a dimension stitched to space so that motion and cause make sense. If we blur those meanings, we talk in circles. So let's separate them and keep the language clean. Imagine filming a ball rolling across a table. The video file is a stack of frames. In any single frame, the ball is still. Motion shows up when frames are ordered and played. In physics, we do something similar. We label events with positions and a clock reading, and time is the label that orders those frames. Real clocks supply the labels. A pendulum swings, a quartz crystal vibrates, a cesium atom flips between two energy states so reliably that we define the second by counting those flips. In this structural sense, time looks as solid as length. You can carry a ruler and a watch and measure both. Yet even here the ground shifts. Special relativity says moving clocks tick more slowly than clocks at rest relative to you. General relativity says clocks deeper in a gravitational field tick more slowly than clocks higher up. Put a lab-grade clock in the basement and another on the roof, and the roof clock wins a tiny race over months. Put a clock on a jet and it comes home disagreeing with the one on your desk. These are not cute paradoxes, they are measured facts, and your phone's GPS works only because engineers correct for them. That tells us time is not a universal beat echoing through the cosmos. It is local and flexible, bound up with motion and gravity. That flexibility tempts many physicists to adopt the block universe picture. Space-time contains past, present, and future all at once like a fixed landscape, and your sense that now is sliding is more like a reading lamp moving along a printed page than a river that carries you. But your life does not feel like a fixed page. You remember the past, but not the future. You can easily scramble an egg, but cannot unscramble it. Your coffee cools, but never steals heat from the room and warms itself. This one-way feel is the arrow of time, and the simplest reason we have for it is statistical. Entropy tends to increase because there are many more disordered microstates than ordered ones, and our universe seems to have begun in an exceptionally low entropy state, so history is the long roll downhill. That answers why a direction, but not why does it feel like a flow. Here, neuroscience adds a quiet clue. The brain builds a smooth present by stitching signals over short windows, tends to predict a little ahead, and writes memory with delay and effort. The moving now may be in part a construction that helps a prediction machine keep you alive. Still, even if the flow is a mental gloss, the ordering is not optional. Causes must lie inside your past light cone, signals cannot outrun light, and relativity's geometry guards the rule that effects do not arrive before causes in any local frame. So a clean starting claim looks like this. Time as a measurable coordinate is real but pliable. Time as a felt flow is likely a brain-level story layered on top of change. The arrow is a statistical result of low entropy beginnings, and the deep open question is whether the world's basic laws truly need time at their core, or whether time itself might emerge from something more primitive. In the acts to come, we will unpack each thread gently: how relativity ties time to space, why gravity slows clocks, how entropy writes direction, what present could mean if space-time is a block, how some theories try to build time from timeless ingredients, and how all of this fits with the elastic minutes you feel when you are bored or thrilled. For now, keep one simple picture in mind. Time is the way the universe keeps books on change. Whether that ledger is printed at the base of reality or written by higher-level processes is the heart of the debate we are about to explore. To see why time cannot just be a universal drumbeat, picture a simple light clock, two mirrors facing each other with a single flash bouncing up and down between them. One round trip is a tick. If the clock sits still on your desk, the flash goes straight up and down. Now imagine the clock gliding past you on a smooth train. Between one mirror hit and the next, the whole device has moved sideways, so the flash must travel a longer diagonal path. The speed of light is nature's speed limit and doesn't change, so a longer path at the same speed means a longer tick. From your viewpoint, the moving clock runs slow. That's time dilation, and it's not a trick of the eye. Fast muons born in the upper atmosphere live longer than they would at rest and reach the ground because their internal clocks tick slow while moving. Swap views and the train rider says your desk clock is the one that runs slow. Who is right? Both, because motion is relative, and the rules treat both observers the same. The deeper shock is not clocks slow down, it's why they slow down. The structure of reality forces everyone to agree on light speed, and the only way to keep that agreement is to let space and time mix. You trade a little time for a little space depending on how you move, like converting dollars to euros. This is the meaning behind space-time. It looks exotic until you use it. Ask a standard, who first? Question. Two lightning bolts strike the ends of a long platform. A person standing midway on the platform sees the flashes at the same time and declares the bolts simultaneous. A person riding a passing train sees the flash from the front strike earlier than the rear. Because the train is moving toward one flash and away from the other, no one cheats. Both use honest light and honest distances. The verdict at the same time is simply not absolute. That alone ruins the idea of a single, cosmic now. Still, physics needs something solid to keep cause before effect. That something is the light cone, the set of places light could reach from an event, and the places that could have reached it, causes must lie in your past light cone. Your actions can only influence your future light cone. The order of events inside each other's light cones is fixed. The fuzziness only appears for widely separated events that cannot influence each other anyway. That is how nature guards logic while tossing out a universal present. The most honest definition of time in this setting is not what a faraway master clock says, but proper time. What your wristwatch records along your own path through space-time. Two travelers who start together and reunite will not generally agree on how much time passed for them. Their paths bent differently through space-time. The famous twin paradox becomes plain in this language. One twin cruises at high speed and turns around to come home. The at-home twin ages more. There is no real paradox because the traveling twin's path includes accelerations at the turnaround, which break the perfect symmetry of constant motions in practice. Pilots, satellites, and even clocks lifted to mountaintops show these differences. General relativity deepens the story by tying time to gravity. A clock deeper in a gravitational well, closer to a massive body, runs slower than one higher up. Shine light upward from the surface of a star, and it climbs out slightly redder because the emitting clock was slow on Earth The effect is tiny but measurable. An atomic clock on the floor ticks more slowly than one on a shelf. GPS satellites carry both special and general relativistic fixes. Their clocks would drift meters per day in position. If engineers did not correct for motion and altitude, everyday life quietly proves that time is flexible. What does all this say about our big question? First, time is not a universal river carrying everything along at the same rate. It is more like a local fabric sewn to space, stretched by motion and sagged by gravity. Second, there is no single global present moment to which the universe pins events. Simultaneity depends on how you move. Third, despite this flexibility, causality stays safe because light cones set the permitted order of influence. In this view, time is as real as distance, measurable, physical, and indispensable. But its reality is different from the thing your intuition wants. Your now is a slice you take through space-time, not a cosmic heartbeat. Your aging is the proper time of your path, not a number that everyone shares. The flow you feel may be a story your brain tells to keep your experiences in order, but the ordering itself is rooted in the geometry of space-time. We'll carry this forward by asking why there is a direction to that ordering, why coffee cools, not warms, and how entropy and low entropy beginnings write the arrow you live by. When you ask why time flows, the cleanest answer starts in the kitchen. You can scramble an egg, but you never watch the scrambled mess leap back into a neat raw egg. Your coffee cools, but it never steals heat from the room and warms itself. These are examples of the arrow of time, and the simplest explanation we have is statistical. Think of a state two ways. A macro state is what you notice with the naked eye. Coffee mixed, egg scrambled, room temperature. A microstate is the exact arrangement of all the molecules. For any neat macrostate, there are very few matching microstates. For a messy macrostate, there are astronomically many. That mismatch, few neat possibilities, many messy ones, makes entropy a kind of counter for how many microways fit this macro look. Left alone, systems move from rare, special arrangements to common, typical ones simply because there are more ways to be typical. Heat flows from hot to cold because there are far more micro-arrangements where energy is spread out than clumped cream mixes into coffee because there are far more ways for the molecules to be intermingled than perfectly separated. Nothing in the microscopic push and pull laws forces this. The single collisions are reversible. The direction appears when you count possibilities for huge numbers of particles. So why does the arrow point the same way everywhere? Because the universe seems to have begun in an extraordinarily low entropy state. Early on, matter and light were smooth and simple. From that special beginning, typical behavior carries systems toward higher entropy, and we ride that downhill roll. This also explains why you remember the past and not the future. A memory is a record, a frozen pattern in your brain, on paper, in a photograph. Making records increases entropy somewhere. Neurons fire and dump heat. Cameras consume power. Bits are flipped and later erased. The only direction in which many consistent records exist is from that low entropy start toward higher entropy, which we label as past to future. No records exist from the future, not because the future is forbidden, but because laying down a reliable trail before events happen would require reversing those typical entropy-raising steps. Even clever tricks do not break the arrow. Maxwell's famous demon, who opens a door to sort fast molecules from slow ones, seems to make heat run backward. But to decide which molecules to pass, the demon must measure, store, and later erase information. That bookkeeping step costs energy and raises entropy overall. The demon pays the bill. At tiny scales, you sometimes do see entropy decrease for a moment. Random jostling in a few molecules can push heat the wrong way briefly, but the odds of a big decrease in a large system are so tiny you would wait longer than the age of the universe to witness it. Here is the key balance. The deep equations for particles do not contain a preferred time direction. They can be run forward or backward. The arrow you live by emerges because the universe started out special, and because counting overwhelmingly favors disorder over order as systems evolve. Your sense of time's flow is your brain's way of narrating that one-way drift while it builds and updates records. None of this makes time fake. It says the direction you feel is not a separate law of nature, but a consequence of initial conditions plus statistics. If the early universe had been high-entropy chaos, there would be no reliable arrow, no durable records, and no stable memory, no story to tell. Instead, we got the rare, tidy start that lets stars, planets, eggs, coffee, and minds appear in that world. The future is the side where entropy is higher, and every cooling cup and every photograph quietly points the same way along the line we call time. When we say right now, it feels like a clean slice through the whole universe. Your room, the moon, a star in Orion, all sharing the same moment. Relativity quietly breaks that picture. Because light has a finite speed and simultaneity depends on motion, two observers moving differently will disagree about which faraway events are now. There is no master clock stamping the cosmos. What does exist is a local now, along your own path through space-time, your world line. Your wristwatch carves a perfectly good personal time called proper time. You can share a now only with things you can directly touch or signal essentially instantly, which outside your immediate surroundings you can't. People sometimes push back and say, surely the universe has a natural slice. What about cosmic time, the time kept by galaxies drifting with the overall expansion? That works as a rough, large-scale bookkeeping choice. Cosmologists often use it, but it collapses in detail near heavy objects where gravity warps time differently, and it still isn't a unique, absolute present. Philosophers map the options with three labels. Presentism says only the present is real, the past is gone, the future doesn't yet exist. Eternalism, the block universe, says past, present, and future are equally real. Your sense of flow is a feature of minds, not space-time. The growing block view splits the difference. The past and present exist, the future is open, and the block keeps adding new layers. Physics does not hand us a definite winner, but its equations lean toward the block picture because they do not single out a moving present. They evolve states smoothly, whether you run them forward or backward. Still, your felt present is not meaningless. The brain stitches a specious present, a small window, on the order of tenths of a second, over which it binds sights, sounds, and touch into one coherent scene, and it keeps updating predictions a beat ahead. That construction is why you experience a crisp now. But the fact that your now is constructed does not make it fake any more than color is fake. It is a reliable summary of local reality, not a global feature of the universe. There is one more tempting loophole: the cosmic microwave background. The afterglow of the Big Bang defines a frame in which its glow looks the same in every direction. Could that pick out a universal rest, and thus a universal now? It picks out a convenient reference, yes, but not a law. Local gravitational wells and motions still skew clock rates, and the rule no influence faster than light still blocks any global synchronizing that all observers must accept. The tidy conclusion is spare and useful. The present is local. A thin neighborhood around you where agreement is possible to within light travel times and clock precision. Beyond that, now depends on who asks and how they move. The big equations get along fine without a sliding universal present, and nothing you measure forces one into existence. What you can count on are causal order and proper time, what your clock reads along your path. In the acts ahead, we'll lean on that local view to explain why gravity slows clocks, how black holes stretch time, and why none of this violates the everyday arrow that makes eggs break and memories point backward. Einstein's key idea folds into a single room with no windows. If you can't tell whether you're feeling weight because a rocket is pushing your floor up, or because a planet is pulling you down, then acceleration and gravity are locally the same thing. That little swap explains why clocks run differently at different heights. Picture a light clock. Two mirrors with a flash bouncing between them. One round trip is a tick. In a rocket accelerating upward, a flash sent from the lower mirror to the upper meets a ceiling that's moving toward it, so the flash arrives a bit bluer, higher frequency. Now swap to gravity. Put the same clock in a gravitational field, lower mirror near the floor, upper near the ceiling. Light climbing against gravity loses a tiny bit of energy and arrives redder, lower frequency. Frequency is just how many crests per second. If fewer crests hit the upper mirror each second, yet the speed of light is still the same for everyone, the only fix is that the seconds upstairs are longer than the seconds downstairs. That's gravitational time dilation in a sentence. Higher clocks tick faster than lower ones because gravity stretches time. You don't need a black hole to see it. Put a lab-grade atomic clock on the floor and an identical one on a shelf. After months, the shelf clock is ahead by a hair. Carry one up a mountain and you age a touch faster than your twin at sea level. Fly a precise clock around the world and it comes home disagreeing with the one on your desk. Part of the shift is motion, special relativity. Part is altitude, general relativity. None of this is thought experiment anymore. GPS only works because engineers pre-correct satellite clocks for both effects, or your location would drift by hundreds of meters per day. Gravity's slow time signature shows up in light too. A photon that climbs out of a gravitational well emerges redder. Gravitational redshift, first measured over a tower on Earth and later around dense stars. When light passes near the Sun, the path and the schedule both bend. The Shapiro delay is a tiny, real late arrival because clocks near mass tick slow trade light for you. If you hover safely far from a black hole and watch a friend's clock being lowered, you'll see their tick slow, their signals redden, then fade. From your distant perch, their time stretches toward a halt as they near the horizon. In their own local story, nothing freezes at the horizon. Proper time along their path stays normal. But space-time's geometry prevents any signal from climbing out once they cross the region where all future light paths tilt inward. This slow time near mass is what we usually call gravity. Not a tug on invisible strings, but a reshaping of the grid on which events sit. Meters and seconds curve in just the way needed to keep the speed of light the same for everyone and to keep cause before effect. The same logic ties into the planet under your feet. Earth's interior, crushed and hot, runs on clocks that, in principle, tick infinitesimally slower than clocks in the air above. Stand up, and your head's clock runs faster than your feet's, by about 1 part in 10 to the 16th power. It's absurdly tiny, and precisely what the theory says. Geodesists even treat height as a surface where clocks tick at the same rate, the geoid, a level at which water rests and time flows evenly. The practical lesson is clean. Gravity is slow time. The closer you sit to mass, the fewer ticks your watch will log compared with a matching watch higher up. On Earth, the shift is small but measurable. Near compact stars, it becomes dramatic. Near black holes, it rules everything. And that circles us back to the big question in this series. The feeling that time flows may be a construction your brain uses to stitch sensations into a smooth present, but the rate of that flow is a testable fact set by the shape of space-time. Motion stretches it, gravity sags it, and clocks, human, quartz, or atomic, quietly report the truth. In quantum theory, time plays a strangely humble role. In the basic rulebook, the Schrödinger equation, time is just an external label, the t that tells a wave function how to change. Give me the state now, and I'll tell you the state a moment later. Position, momentum, spin, energy. These are quantum observables with operators you can, in principle, measure. But there is no standard time operator, the same way there is a position operator. That asymmetry matters. People often quote an energy-time uncertainty principle as if it were the twin of position momentum. It isn't. For position momentum, the uncertainty is baked into the mathematics of two operators that don't commute. For energy time, time isn't an operator at all. The rule is a family of trade-offs. To pin down an energy very precisely, you must watch the system for a long duration, and short-lived quantum states carry a fuzziness in energy that shows up as line width in spectra. You see this every time an excited atom emits light. The shorter its lifetime, the broader the color it produces. So time, in textbook quantum mechanics, is a parameter we bring from outside, not something the system itself spits out as a reading. And yet, our best clocks are quantum machines. An atomic clock is just a very regular quantum transition, an electron jumping between two energy levels, turned into ticks. The more stable and higher frequency the transition, the better the clock. That is why modern optical lattice clocks, which count light frequency ticks of atoms like strontium, now keep time so steadily that if one had started at the birth of the universe, it would be off by less than a second today. Their limits aren't bolts and springs, they are quantum noise, randomness in the outcome of many identical atomic coin flips. We squeeze that noise with tricks like spin squeezing, entangling many atoms so their collective uncertainty shrinks in the useful direction. And we have made clocks so sensitive they see gravitational redshift over a vertical millimeter. Raise the clock and it ticks measurably faster because it is higher in Earth's field. That is quantum hardware reporting general relativity in a tabletop lab. Deeper down, some proposals say time might emerge from relationships inside a big quantum state, rather than exist as an external given, and famous sketch is the Page-Wouters idea. Carve the universe, on paper, into two parts, a clock and the rest. Tie them with entanglement, and you can recover an effective flow. Subsystems change relative to the clock, even if the global state is, in a certain precise sense, timeless. Quantum gravity hints at the same mood. When you try to write a wave equation for the entire geometry of the universe, you bump into forms, like the Wheeler-DeWitt equation, where the usual time parameter drops out. What evolves is relational structure, not an absolute tick. None of this is settled. They are working theories, but they point to a clean theme. In quantum mechanics, we do not measure time the way we measure position. We build time by comparing changes. This atom's phase against that atom's phase, this oscillator against that one, and the best such comparators are quantum. That gives you a practical and a philosophical answer in one breath. Practically, timekeeping is a quantum craft. Stabilized lasers, cold atoms, entanglement, and careful counting. Philosophically, time in the equations looks less like an ingredient of the soup and more like the label on the ladle we use to stir it, until perhaps we zoom out to the whole pot and recover time as the pattern that links parts to parts. However you slice it, the same lesson returns. The flow you feel is partly a brain story. The rate your clock reports is physics. And in the quantum world, clocks are not a background. Clocks are systems made of the same quanta as everything else, telling change by changing. Time travel to the past makes gripping stories, but the real universe stacks the deck against it from several angles at once. Start with causality and relativity. Every event sits inside a light cone, the set of places it can influence, future cone, and be influenced by past cone. If you could send a signal faster than light, different observers would disagree about which came first, letting an effect arrive before its cause. That is a recipe for contradictions, and nature has never shown us a way around it. No tachyons, no superluminal messengers, and quantum entanglement, while spooky, does not carry controllable information faster than light. On the other hand, the equations of general relativity do admit exotic spacetimes with closed time-like curves, paths that loop back into their own past. Famous examples include Gödel's rotating universe, an idealized infinitely long spinning cylinder, Tipler, certain carefully arranged wormholes, and the inner regions of a perfect spinning, Kerr black hole. On paper, a traveler could trace one of these loops and meet their earlier self. But each case depends on conditions our universe does not appear to supply, or it becomes violently unstable once you include realistic physics. Gödel's model needs global rotation we do not observe. The cylinder must be truly infinite and spin absurdly fast. Traversable wormholes require sustained negative energy density to hold their throats open. Tiny negative energies occur in special quantum setups, like the Casimir effect, but quantum inequalities severely limit their size and lifetime. Try to stabilize a wormhole, and quantum fields pile up at the mouth, blasting it with radiation dive toward the tiny interior of a spinning black hole, and you face a blue shift avalanche of incoming light and particle fields at the inner horizon, likely turning the region into a destructive singularity. This pattern inspired Hawking's chronology protection idea. The laws conspire to prevent loops that would allow paradox. There is a softer escape hatch called self-consistency, Novikov. If a loop exists, events on it must be globally consistent. You can visit the past, but you cannot change it. Whatever you do already happened. The note you received last week is the one you will write tomorrow. The gun jams every time you try to create a contradiction that avoids logical breaks, but it also drains the freedom that makes time travel tales enticing. Quantum ideas add two more twists. In many world-style thinking, an attempted paradox could shunt you into a different branch. No contradiction, because the branch where you warned yourself is not the branch you came from. Tidy, but it does not produce a device that sends actionable messages to your own past. In other approaches, once quantum fields and gravity are treated together, would-be loops destabilize and evaporate before they can form. Add thermodynamics and the fence gets higher still. The arrow of time we live by comes from low entropy beginnings and the overwhelming odds that disorder grows. A machine that reliably makes effect before cause would have to swim against that statistical river everywhere it touches the world, laying down records before events and erasing heat in reverse, which is not how large systems behave. Put the threads together and the verdict is blunt but useful. Relativity guards local cause and effect with light cones. Quantum theory offers no handle to steer signals backward. Exotic loop solutions demand unphysical matter or blow up under quantum back reaction. And the entropy arrow makes everyday paradox machines fantastically unlikely. Could a deeper theory someday rewrite this? Maybe, but every advance so far has raised the price of a past-warred tunnel, not lowered it. For a working rule of reality, nature defends causality, and the harder you try to fold time back on itself, the more fiercely the equations push you away. Time in physics is a coordinate on a map, but the time you feel is a construction built on delays and guesses that your brain hides from you so the world seems smooth. Signals from eye, ear, skin, and joints arrive late and at slightly different speeds, so the brain collects them into a small window, the specious present, roughly a few tenths of a second, then edits and backdates events so they line up, which is why a dropped plate seems to shatter as one thing, even though light, sound, and touch reached you at different moments. Within that window, attention and arousal act like a throttle on an internal ticker, a pacemaker in simple models. So when you are stressed, afraid, or excited, the ticker runs fast and a short interval feels long. Think roller coaster climbs or near-miss traffic. While low arousal, boredom, routine, lets the ticker idle and long intervals feel short in hindsight. Memory adds another twist. When you judge a period after it ends, your brain uses memory density as a proxy. More novel events laid down equals that took a long time. Fewer events equals that flew by, which is why a first day in a new city feels long. But weeks of the same commute blur together, and why life seems to speed up with age as novelty drops and the brain compresses familiar days. Attention flips the effect prospectively. Stare at the clock and seconds crawl because you are counting ticks in the moment, but get absorbed in a task and the ticks go uncounted, so hours disappear. Your senses also play timing tricks that reveal the editing. The stopped clock illusion, chronostasis, makes the first second after you shift your gaze feel longer because the brain fills the gap created by a rapid eye movement with the new image and backstamps it, and the oddball effect makes a single unusual beep or flash seem to last longer than matching ones before and after because novelty spikes arousal and attention. Even the sense of cause is massaged by timing. Temporal binding pulls an action and its outcome closer in perceived time, so your button press and the beep seem to belong together, helping you link causes to effects in a noisy world. Body state matters too. Faster heart rate, higher temperature, or stimulants like caffeine can speed the internal ticker so intervals feel longer, while fatigue, sedation, or cooling can slow it so intervals shrink. Rhythms set a slow frame. Your circadian clock drifts if you hide it from daylight, and that daily rhythm nudges how alert or sluggish your short-term timer feels across a day. At the fine scale, your brain also predicts ahead, so moving objects look slightly farther along their paths than raw delays would allow, the flash lag effect. And your ears predict the next beat in music, so a perfect metronome can feel late if your attention slips. Importantly, these are not failures, but features. The world would seem jumbled without this smoothing and prediction, and a small timing bias is a good trade for continuity. You can nudge the system, add novelty to slow the life blur, vary routes and routines, step outside in daylight to anchor the circadian clock, use breath or pulse as a gentle metronome to steady anxious, fast time, or structure tasks into clear chunks, event boundaries, so the day leaves more memory traces and feels fuller. Tie this back to the bigger question, and the picture is clean. Physics gives you a local, flexible time measured by clocks that never agree perfectly. Thermodynamics gives you a direction from lower to higher entropy, and the brain gives you a felt flow built from integration windows, attention, arousal, and memory. That is why a minute in a dentist's chair stretches and an hour with a friend vanishes, even though the same wall clock kept both. Your nervous system is not reporting raw seconds, it is translating change into a stable story, smoothing delays, predicting a little ahead, and then filing the result in memory with a bias for novelty. In short, The flow you feel lives in your head and serves your survival, while the rate a lab clock reports lives in the world and serves navigation and cause, and both can be true at once without contradiction. When cosmologists say the universe is about 13.8 billion years old, they are not reading from a master wall clock hanging over the cosmos. They are using a convenient, large-scale clock that only works because the universe looks nearly the same in every direction when you average over big enough distances, and because galaxies, on that grand scale, drift with the general expansion rather than tearing off on their own. In that smooth picture, the FLRW model if you want the formal name, you can imagine a crowd of ideal coasting observers carried by the expansion, each with a perfect local clock, and you set cosmic time by asking how much proper time those observers have experienced since the hot, dense beginning. That slice-by-slice bookkeeping is useful, but do not confuse it with a universal present. Near heavy objects, gravity still warps clock rates. In crowded regions, motions and fields break the smoothness, and even in the calm void, simultaneity at great distance is still frame-dependent. What this cosmic clock does give you is a clean way to relate three simple things: the universe's size scale, how stretched space is compared with earlier, the redshift of light from distant galaxies, how much its wavelength has been stretched by expansion, and look back time, how long that light has been traveling. Light from a galaxy at redshift Z does not just arrive redder. Its time stretches by the same factor 1 plus z, so distant supernova explosions twinkle and fade in slow motion to us, their light curves literally elongated by cosmic expansion. That time stretch is not a philosophical point. Astronomers measure it, and it is one of the cleanest, least arguable signs that the fabric between galaxies has grown. While the light was in flight, the age number itself comes from fitting many data threads at once. The Hubble expansion rate today, how that rate has changed with time, the pattern of tiny ripples in the cosmic microwave background, the afterglow from when the universe was a hot fog, the way galaxies clump on large scales, and the brightness-distance behavior of supernovas used as standard candles. Stitch those together and you get a history curve. Fast expansion early, a slowdown as matter's gravity tugged inward, and a later speed up as dark energy's push took over. And integrating that curve tells you how much cosmic time has passed for coasting observers since the beginning. It's tidy, but it has limits you should respect. First, horizons. We can only talk about what we can see. Beyond the observable patch lies more universe, not a wall, and our now does not touch it in any physical sense. Second, inhomogeneity. Locally, gravity bends the rules. A clock on a neutron star's surface pays a huge time penalty compared with a clock drifting in intergalactic space. So there is no single rate everywhere, even if you agree on the slicing. Third, coordinates are choices. Cosmic time is the simplest, most natural choice for a smooth universe, but you can slice space-time differently and still describe the same reality. Physics does not elevate one slicing into a metaphysical present. Still, as a working language, cosmic time earns its keep. It lets us say, when the universe was 1 second old, it was a fireball of neutrinos and light. When it was 380,000 years old, atoms formed, and the microwave glow set free. By a few 100 million years, the first stars lit. By a few billion, galaxies matured. And only recently on that scale did dark energy take the lead. It also teaches humility. What you see at great distance is history, not a live broadcast. And the deeper you look, the younger the universe you witness. So cosmic time is real enough to measure and model, but it is not a cosmic heartbeat you can sync across every crater and quasar. It is the calm, large-scale ledger of an expanding world, useful precisely because it ignores the small, messy places where gravity and motion make clocks disagree, and honest enough to admit that now, beyond your neighborhood, is always a matter of how you choose to cut the map. Physics gives us proper time, what your own clock measures along your path, and cosmic time, a smooth ledger for the expanding universe. But your watch follows neither. It follows a human-made compromise called civil time, stitched from quantum ticks, Earth's wobbly spin, and global agreements. And the seamwork matters if you want phones, planes, and power grids to agree on now. The unit itself, the second, isn't tied to sunsets. It's defined by nature. Exactly 9,192,631,770 oscillations of a microwave transition in cesium-133, because that jump is stable everywhere and every when we've checked. National labs count those ticks with atomic clocks, compare them by fiber links and satellites, and average the results into a continuous, never-stopping scale called TAI, International Atomic Time. TAI is clean physics, but the planet you stand on is messy. Earth does not spin like a metronome. Tides tug, winds trade momentum with the crust, earthquakes twitch plates, and the core sloshes. The length of day wanders by milliseconds, and over centuries the moon's tidal breaking slowly lengthens it. If we let civil clocks follow only cesium, noon would drift off the sun's sky. To keep the wall clock roughly in step with the planet, the world uses UTC, Coordinated Universal Time, which tracks TAI, but occasionally inserts a leap second so UTC never strays more than a whisker, under a second, from UT1, a measure tied to Earth's rotation. Leap seconds are odd. They don't come on a regular schedule, they add a 23:59:60 when needed, and they stress computer systems that expect every minute to have exactly 60 seconds. Some networks hiccup when that extra tick appears, which is why engineers rehearse the event and large services smear the leap by stretching milliseconds across a day. There's also GPS time, a satellite system's steady clock that never inserts leap seconds at all. Receivers convert GPS time to UTC by applying an offset broadcast in the signal, which is why your phone knows the time even if your city changes its daylight saving rules late. Underneath the app's live time protocols, NTP over the internet, PTP on precise networks, steering millions of less than perfect oscillators, so routers stamp packets, markets match trades, and antennas beam in phase. Meanwhile, relativity hasn't gone away. Satellite clocks tick faster high above Earth and slower because they move, so their hardware is preset and software corrected. Fiber links carrying timing across mountains must account for gravitational potential differences, so picoseconds don't drift into nanoseconds. Time zones and daylight saving are pure politics layered on physics. Zones carve longitudes into human blocks, and clock changes shuffle social schedules without changing the sun. So 7 p.m. is a treaty between your city and the sky. Because leap seconds are painful and the drift they fix is tiny, standards bodies have agreed in principle to phase them out in the 2030s and let UTC run smoothly. If that sticks, civil time will slowly walk away from solar time by a second every few years, a difference ordinary life won't notice for centuries, while astronomy and navigation will apply small, explicit corrections. Step back, and the picture is tidy. Your sense of time is a brain-made flow. A lab second is a quantum tick. Gravity and motion make local rates bend, and the time your phone shows is a negotiated weave of all three, engineered so the lights stay on, the maps line up, and people meet at the same minute, even if the planet, the network, and the cosmos disagree about what now should be. People talk about the arrow of time as if there were only one, but in practice we meet several arrows that all aim the same direction, and the reason they line up turns out to be simple once you keep the picture big. The universe began in a very special, low entropy state, and everything we do happens while rolling away from that start. The thermodynamic arrow is the everyday one. Entropy, a count of how many microscopic arrangements fit the same macroscopic look, tends to grow, so cream mixes into coffee, heat spreads, cups shatter, and we do not see the reverse, because the reverse would require threading a path through an astronomically tiny set of microstates. The psychological arrow follows along because making memories, writing notes, and laying down synapses all generate waste heat and increase entropy. You remember the past because records exist in the present, and records exist because processes have already run downhill. There is also a radiative arrow in electromagnetism. Maxwell's equations allow wave patterns that spread outward from a spark, what we see, and patterns that seem to converge inward on a point as if emitted from the future, what we never see. The math treats both, but the world picks the outward kind because of boundary conditions. The environment around us is full of warm matter and cool empty space, not a fine-tuned bath of coordinated incoming waves, and that statistical tilt, more ways to be messy than laser precise, selects radiation that flows from sources to space. The causal arrow in relativity is geometric. Light has a speed limit, so events split into those that can still affect you, inside your past light cone, and those you can still affect, inside your future light cone. That local order is rock solid, even though far away now is fuzzy. Signals cannot hop outside their cones without breaking cause and effect. Quantum theory adds two related arrows that look mysterious until you fold in the environment. One is the measurement arrow. We prepare a neat quantum state and later we find a definite outcome. The math between is time symmetric, but interacting with many uncontrollable degrees of freedom. Air, radiation, the measuring device, causes decoherence, which means phases wash out and superpositions turn into stable, pointer facts. We can record decoherence itself is not magic collapse. It is ordinary quantum interaction with a large, noisy world, and it lines its direction up with entropy because it spreads information into countless degrees of freedom that we do not track. The other is the information arrow. Anytime you erase information to reset a memory element or a computer bit, you must dump a minimum amount of heat. This is Landauer's principle. So tidy bookkeeping has a thermal price, and that price is paid in the same direction that entropy grows. People sometimes point to T violation in particle physics, tiny asymmetries in rare decays of kaons and B mesons, and ask whether this is the true arrow. It is not the one you feel. Those effects are real but minuscule. They do not set the direction of coffee cooling or memory making. What ties all the practical arrows together is not a new law, but the initial condition, a smooth early universe with extremely low gravitational entropy, space nearly uniform, matter spread thin, which left room for clumps to form, stars to light, and temperature differences to exist so engines, storms, and brains could run. That special start picks a slope, and once the slope exists, every process that relies on typical behavior, loose radiation, or record making points the same way down it. Even the outliers obey the rule when you zoom out. You can watch a small fluctuation briefly move heat the wrong way in a tiny system, but the odds for big systems are so punishing that no camera will ever catch an omelette unscrambling itself. You can set up clever interference so a wave converges to a point, but only by importing fine-tuned conditions from elsewhere, and making those conditions costs entropy. You can run a reversible computer in principle, but to get useful work done in the real world, you still reset bits and pay the heat bill. Put simply, the thermodynamic arrow gives the slope, the radiative and quantum arrows ride the slope, the causal arrow fences the path, and the psychological arrow is how a prediction-making brain narrates the trip. Different faces, same direction, same reason. When you zoom far enough into our best theories, an odd pattern appears. Time looks less like a basic ingredient and more like a convenient label that shows up when many parts interact and several serious ideas try to make that hunch precise in plain terms. One family is relational. Instead of saying a system changes in time, it says parts of a system change relative to other parts. So a clock is not an external drumbeat, but just one piece we choose to compare against the rest. And if you split the world into clock and thing being timed, you can recover a smooth flow from their mutual dance. That is the spirit of Page-Wouters. The whole, clock plus rest, sits in a static, balanced quantum state. Yet subsystems look like they evolve because they are entangled, correlated, in a way that lets the clock's steady patterns serve as a ruler for everything else. So time is not outside the universe, but a relationship inside it. A second family is timeless gravity. When you try to blend quantum rules with Einstein's curved spacetime, you run into an equation, the Wheeler-DeWitt constraint, that, in simple words, says the total wave of the universe doesn't tick. So the usual T is absent, and what we call evolution comes from tracking how shapes of space and fields co-vary. Ravelli calls this partial observables. Barber talks about Platonia, a landscape of possible arrangements where what we name becoming is a path through a gallery of stills, and duration is just how much change happens between stills you choose as reference. A third thread is entanglement thermodynamics. In many body quantum systems, even when the basic equations are reversible, entanglement between parts tends to grow in typical states, which makes subsystems look as if they are relaxing toward equilibrium. So an arrow of time and a sense of flow can emerge from statistics of quantum correlations rather than from a fundamental ticking parameter, and in modern holography, ADS-CFT, people even relate how much space exists to how much entanglement there is, hinting that geometry, and thus the stage on which clocks live, could be built from informational links. Causal set ideas flip the picture again, postulating that space-time is not a smooth fabric, but a sprinkling of elementary events ordered by cause, like a growing random graph, where time is literally the growth of that order, not a continuous line you can subdivide forever. Shape dynamics trades one kind of symmetry for another and finds a picture where only relative shapes matter, and a global time can emerge under certain conditions. Across all of these, the shared moral is spare. If you remove the habit of imagining a master clock outside the world and instead ask, what changes with respect to what, you often recover the usefulness of time without assuming it up front, which also clarifies why there is no universal now. Different observers carve the relational web differently, picking different subsystems as clocks. None of these proposals is settled law. Each has puzzles, missing links to measurement, and open math, but they help explain why your lab never needs a time operator to make a clock, why cosmology can keep a smooth ledger without declaring a sacred present, and why the arrow you feel lines up with entropy growth rather than with a fundamental one-way law. So the clean takeaway is this: time may not be a thing. The universe has so much as a rule book. We derive when enough pieces move together, a shared yardstick born from comparison, coarse graining, and typical behavior, which is why minutes are reliable on your watch, elastic in your head, and absent from some of the deepest equations until we choose what will play the role of a clock. Ask whether time comes in grains, the way matter comes in atoms, and you meet the number physicists point to first. The Planck time, about 5.39 times 10 to the negative 44th seconds, built from three bedrock constants, the speed of light c, Newton's constant g, and Planck's constant h. It is not a measured tick. It is a scale where our current theories, quantum mechanics and general relativity, both shout at once, telling us that below this scale, our usual pictures of distance, duration and cause likely break down. Pair it with the Planck length approximately 1.6 times 10 to the negative 35th meters, and you get a quantum of geometry vibe. Perhaps space-time is not a perfectly smooth fabric, but a weave that only looks smooth when viewed from far away. Different research programs explore that hunch in different ways. Loop quantum gravity quantizes areas and volumes, suggesting a minimal chunkiness of geometry. Causal set theory postulates space-time is really a growing sprinkled order of elementary events. Some approaches treat space-time as emergent from quantum entanglement, so how much space exists tracks how much information is shared, and time is a parameter that appears with that structure. None of these ideas forces a literal click at the Planck time the way a metronome clicks. They say continuity probably isn't fundamental. Not every process occurs in equal jumps. Could we see discreteness directly? The honest answer is that all clocks we can build behave as if time is continuous to an extreme degree. The best optical atomic clocks resolve fractional differences in tick rate at parts in 10 to the 18th and register gravitational redshift over a vertical millimeter, and yet they do not reveal a flaw, only noise from quantum statistics and technical limits. Astronomers push another way. If space-time were grainy enough to make light of different energies travel at slightly different speeds, high and low energy photons from the same distant flare would arrive with a measurable offset after crossing billions of light years. Careful analyses of gamma-ray bursts and pulsars have not found robust energy-dependent delays, setting tight bounds on simple granularity pictures. Likewise, if space-time were wildly frothy, sharp images of far-off galaxies would blur. Instead, we see interference fringes and crisp patterns that imply any foam is subtler than those crude models. Sometimes people hear discrete time and think of time crystals, so it is worth clearing the fog. A time crystal is not a tiny clockwork that proves time comes in atoms. It is a special state of matter that shows periodic motion without spending net energy, either in a driven steady state, discrete time crystal, or with long-lived oscillations protected by many body effects. It's about symmetry breaking in dynamics, not about a universal smallest tick. Another tempting idea from the 20th century is the chronon, a fundamental time quantum. Neat name, no evidence. Even if space-time is atomized at the Planck scale, relativity's success suggests those atoms cooperate to produce smooth behavior at human scales, just as fluid equations describe water, even though water is molecules. That continuity is not a dodge. It is what every measurement to date supports. Proper time along a path adds up. Redshifts behave as the smooth theory predicts, and cause and effect remains fenced by light cones without jitter. The right way to carry this is plain and modest. The Planck time is a warning sign on the road that says, our present theories are not reliable past this point. Not a roadblock that says, time ends here. The deepest layer may be discrete, relational, informational, or something we have not guessed yet, but until an experiment forces a change, the clocks we build and the skies we read say that time, at accessible scales, is as continuous as a ruler is straight, not perfect in principle perhaps, but straight enough that bridges stand, satellites navigate, and your life can be kept by a second that behaves like a line, not a staircase. Stand far from a black hole with a good telescope and a very patient clock, Lower a small probe toward the dark center on a long cable, and you will watch the probe's signals slow, redden, and fade as it nears the event horizon. From your safe perch, each tick takes longer than the last, as if time itself were being pulled like taffy until the ticking almost stops. And if you cut the cable and let the probe fall, its last bright heartbeat seems to freeze just outside the edge forever, smeared into a thin ring of dim light. That freeze is your view, not the probe's. Along the probe's own path, proper time flows normally, and the crossing happens in a short, calm rush with nothing special locally marking the horizon, because gravity is geometry, not a tug, and the horizon is simply the place where all future light paths point inward. So once you cross it, every path you could take leads deeper, and every message you try to send is bent back. This split view is the essence of black hole time. To distant observers, clocks near the horizon crawl. To infallers, clocks behave. But the set of reachable futures shrinks to one fate. Light tells the same story. A photon launched upward from close to the horizon climbs out redder and later than one launched higher. A pure gravitational redshift that on stars is modest, and at a black hole becomes extreme. Radio pulses from matter spiraling inward stretch until they fade, which is why accretion disks look like hot, bright rings with a dark center. The light that would show the center never gets out in finite external time. Time also shapes orbits. Near the hole, space and time twist together, frame dragging if the hole spins. So a clock on a fast, low orbit can run very differently from a clock parked far away, and that difference is so strong near compact objects that simple "whose is older" games give wild answers. Live fast and low, and you age less than a friend who loiters high. Push past the horizon in thought, and the probe's proper time ends at a singularity, where our current equations predict densities and curvatures beyond meaning. Most physicists read that, not as nature breaks, but as our theory's map ends, a sign that quantum gravity must replace that crashing point with new rules. Until we have those rules, we work with the outside view, and there the most surprising time story is Hawking radiation. When you combine quantum fields with a horizon, the whole glows faintly as if it had a temperature, leaking energy and, over absurdly long times, shrinking. A solar mass hole would take far longer than the age of the universe to evaporate, while tiny hypothetical holes would fade fast. This introduces a deep puzzle about time and information. What happens to the detailed information about what fell in if the hole disappears into featureless radiation? The old worry was, it is gone, which would break the quantum rule that evolution is reversible, but a newer, stronger case built from thought experiments and holography says the information is not lost. It is encoded in very subtle correlations in the outgoing radiation, a view captured in the Page curve, where the entropy of the radiation first rises as the hole emits, then falls as correlations carry the record back out. If that is right, then from a very distant, very patient vantage, the story of what fell in does, in a sense, re-emerge, but never as a tidy playback, more like a whisper spread across many photons. Near-term evidence is indirect. We cannot catch Hawking radiation from big holes yet, but black hole thermodynamics, gravitational wave observations of mergers, and sharp mathematics all point to a consistent picture. Horizons store information in proportion to their area, not volume. And time at a horizon behaves like time in a hot system that scrambles signals quickly but does not erase them. None of this changes the everyday bottom line. Gravity is slow time, and a horizon is the ultimate slow time surface. To you, clocks there almost stop and messages stall. To the traveler, time is normal, but all roads lead inward. Over impossible spans, quantum effects make the edge leak, and the long accounting suggests that what went in is not truly forgotten. And under it all sits the open square on the board, what replaces the singularity when quantum gravity finally speaks. Because that answer will tell us whether the end of time inside a hole is a real ending or just a place where the universe has been refusing to show its deeper clockwork. If most microscopic laws look the same run forward or backward, how can physicists also say time reversal symmetry is slightly broken? The short answer is that a tiny slice of nature, the weak force, treats forward and backward differently in rare reactions, and we've caught it in the lab, but the effect is so small and so specialized that it does not set the everyday arrow that makes cream mix into coffee. Here's the calm version. Take almost any basic equation for colliding billiard balls, light bouncing off a mirror, or atoms trading energy. And if you flip the sign of time and also reverse momenta, the movie is allowed by the rules. If you prepared the mirrored starting conditions, the reverse would happen. The weak force, which governs certain radioactive decays, is quirky. It already violates parity, left-right mirroring, and it also violates CP, mirror plus swapping particles, with antiparticles. A famous theorem says if CP is broken, then T time reversal must be broken too, so that the combined CP-T symmetry stays intact. We see CP violation directly in neutral kaons and B mesons. Particles and antiparticles decay into final states at slightly different rates or with different interference patterns. Dedicated experiments built for this, think of huge detectors watching factories of short-lived mesons, have mapped those tiny skews with high confidence. That is the T violation you hear about. It means the exact pattern of probabilities in some subatomic processes is not identical in a frame-reversed movie. But nothing in those decays lets you build a machine that makes heat flow from cold to hot or turns a scrambled egg back into a raw one. Why? Because the macroscopic arrow comes from statistics and initial conditions. There are vastly more ways to be mixed than separated. And because the weak force's oddness is overwhelmed by electromagnetism and the strong force in ordinary matter. Think of T violation as a faint accent in a whisper inside a stadium. The stadium's raw, entropy, sets the direction you hear. Still, that whisper matters for a deep reason. The universe today is made of matter, not equal parts matter and antimatter. To make such an imbalance from a symmetric beginning, three broad ingredients, Sakharov's conditions, are needed. Processes that do not conserve baryon number exactly, departure from perfect thermal equilibrium, and CP, therefore T violation. We have all three in principle, but the amount of CP violation in the known quark physics seems too small to explain the vast cosmic tilt toward matter. That is why huge experiments are chasing CP violation in neutrinos, and why ultra-sensitive searches hunt for an electric dipole moment in the neutron, electron, or atoms. A permanent dipole would be a clean sign of new CP violating physics. So far, the dipole searches come up empty, setting brutal upper limits. Neutrino experiments hint at interesting phases, but have not closed the case. If extra sources of CP/T violation exist, and many suspect they do, they might live at higher energies or in sectors we've only glimpsed. Notice one more guardrail. All credible roads keep CP-T intact. That combined symmetry is welded into the structure of quantum field theory. Breaking it would shred too much else, so the picture you should carry is tidy and two-layered. At the ground floor, the equations of the familiar forces are largely time-symmetric, and the weak force adds a tiny measured twist. At the lived-in floor above, the arrow of time points from low to high entropy because of how the universe started, and because counting possibilities overwhelms any microscopic quirk. The weak twist may help explain why there is anything here to drink coffee at all. matter winning over antimatter. Yet it does not tell the coffee which way to flow. In that split lies the answer to a common confusion. Time reversal violation is real, precise, and subtle. The arrow you feel is broad, statistical, and ruthless. The worry goes like this. If relativity encourages a block universe where past, present, and future all sit together in one four-dimensional map, then everything that will happen is already there. So choice is an illusion. But this takes a visual metaphor too literally and confuses three separate ideas: determinism, predictability, and control. Start with determinism. Many useful models, planet orbits, ideal gases, are deterministic, yet quantum mechanics is not. When you measure, outcomes come with built-in probabilities that no one can beat. Even if you imagine a deeper layer restoring determinism, Bell test experiments tell us any such layer must be non-local or give up other comfortable assumptions. So physics does not force hard determinism. Next, predictability. Even in purely classical systems, chaos makes long-term prediction fail because tiny unknowns balloon into different futures. You cannot measure initial conditions with infinite precision, and you cannot compute infinitely fast. So what will happen is often unknowable in principle to any finite agent. Limits from computation and thermodynamics bite here too. To predict the world perfectly, you would need a copy of the world at least as large as the world, running faster than the world, dumping heat somewhere else. There is no room outside the universe to hold that simulator, and inside it you cannot outrun the thing you are simulating without paying an energy and entropy price. Finally, control. Agency is about whether different actions available to you would lead to different outcomes in your future light cone. That question is asked within physics all the time using interventions. Hold the past fixed up to now, swap one setting for another on a device, and compute how the probabilities of later events change. If those probabilities differ, the setting is a real causal handle. Nothing in relativity forbids that. The block picture simply says the whole web, including your deliberation, neurons, muscles, and the downstream effects, forms one consistent tapestry. Inside the tapestry, there are true counterfactuals. If the patch representing "you press the brake" is different, the patch representing "car stops" is different too. The fact that both patches exist in the finished picture does not erase the local fact that only one runs along your actual world line. Useful way to think about this is compatibilism in physics language. Laws can be time-symmetric and still support an arrow because of boundary conditions. The universe began in low entropy, so records, memories, and reliable control all point from earlier to later. Within that slope, the macroscopic patterns we call agents compress information about their past, forecast branches of possible futures, and select actions that bias. Which branch becomes actual? That selection is not supernatural. It is what control circuits and brains do when they exploit regularities in their environment. Quantum mechanics adds a different flavor of openness. When outcomes are genuinely probabilistic, could have done otherwise is not just epistemic. Identical preparations can yield different results, and choices can steer probability distributions without violating any conservation law. None of this makes choice magical. It makes it physical. You are a thermodynamic machine that burns free energy to acquire information, reduce uncertainty about near futures, and push on actuators in time to matter. Relativity sets the fence posts. No influence outside light cones, clocks disagree depending on path, but inside the fence, it leaves causation intact and local. The block metaphor is best used as a bookkeeping tool that respects those fences, not as a cosmic doom. saying nothing can ever be different. If the world were rewound to exactly the same microstate, the same movie would play, including your reasons and acts. If the world up to now were held fixed, but your current control variables were set differently, later frames would differ in the ways those controls reach. That is enough for agency to be real in the only sense that matters for living beings. The ability to use information in the present to shape probabilities in the future within the lawful limits of space-time. Physics gives you seconds on a watch, but your cells keep their own time with a layered set of oscillators that rarely line up perfectly with civil clocks, which is why you can feel out of time even when the wall clock is right. At the top sits a master pacemaker in the brain called the suprachiasmatic nucleus, or SCN, a rice-sized cluster that listens to daylight through special retinal cells sensitive to blue cyan light and then sends timing signals, hormones, nerve pulses, temperature nudges across the body. In every organ, smaller peripheral clocks tick with the same basic design. Feedback loops in clock genes and proteins. You can think of them as biochemical pendulums that take a little over 24 hours to cycle. Light is the main Zeitgeber, time giver. But meals, exercise, social cues, and even drugs also shift these clocks. That is why a late heavy dinner or a midnight workout can push your sleep-wake phase even if you sat under bright lamps all day. When the SCN and peripheral clocks disagree, after a long flight, a night shift, or a weekend drift, you feel jet lag, groggy, hungry at odd hours, unfocused. The fix is not complicated in principle. Land your light, food and activity at the same local times each day, and the clocks resynchronize. In practice, it takes days because different tissues shift at different speeds. The gut and liver lag the brain, and the SCN changes phase only so fast. Chronotype, the natural early bird or night owl tendency, adds a built-in offset. Forcing an owl onto a lark schedule, or the reverse, creates social jet lag, the weekday-weekend whiplash that leaves many people underslept. Circadian clocks also gate performance and risk. Reaction time, strength, insulin response, pain sensitivity, even asthma and heart attack likelihood show daily patterns. So same-hour tasks can feel very different depending on where your internal day is. The other body timer is slower, biological age. Cells accumulate chemical marks on DNA and proteins. Damage and repairs leave small scars, and tissues adapt to stress. Together, these changes let scientists build epigenetic clocks that often predict health risk better than birthdays do. Two people with the same chronological age can have different biological ages. Chronic sleep loss, shift work, inactivity, and long stress can push the slow clock forward, while regular daylight exposure, steady sleep timing, movement, decent diet patterns, and strong social ties tend to pull it back toward the calendar. Telomeres, the protective end caps on chromosomes, shorten with many divisions, but they are only one piece of the aging mosaic. The broader picture is that biology keeps a ledger of wear and repair that your choices can influence but not fully reset. Temperature adds a subtle twist. Most chemistry races faster when warm yet circadian clocks are temperature compensated. They hold roughly 24 hours across a range, so the body's timing stays useful year-round. Still, a small daily drop in core temperature at night is part of what helps you fall asleep, and artificial heat or late workouts can delay that drop and shift your phase. The punchline for our theme is clean. Time in your head, the sense of flow, comes from neural windows and attention. We explored that already. Time in your body, the circadian and aging layers, comes from self-running oscillators and slow molecular bookkeeping that respond to cues but never perfectly track wall clocks. Time in physics, the proper time on a path, ticks a hair faster at your head than your feet, and a hair slower on a jet than at home. Those relativistic differences are real but tiny compared with the hours your body clock can gain or lose with light and routine. If you want your personal now to feel steady, you nudge the biology. Morning daylight for phase anchoring, a consistent sleep window, earlier meals when you need to shift earlier, exercise timed to the day you want to live, dimmer light in the last hours before bed. None of that changes space-time, but it aligns your internal metronomes, so the seconds your watch counts line up with the day your cells expect and life stops feeling out of phase. If relativity says there is no universal present because signals take time, the internet is a giant laboratory that relearns that lesson every millisecond. Computers are separated by distance, messages crawl through fiber at 2/3 the speed of light, cues jitter, and each machine's hardware clock drifts a little because its quartz crystal is a tiny imperfect metronome, so there is no single exact now that every server can share. What we do instead is engineer truce after truce. A basic clock on a machine counts oscillations and divides them down into seconds, but crystals wander by tens of parts per million with temperature and age, which means two lonely servers can differ by seconds after days. Network time protocol smooths that by having clients ping time sources, measure round-trip delays, and adjust both the offset, how far ahead or behind, and the rate, how fast the local clock runs, blending several sources to ride out bad links. It is good to the millisecond across the open internet and far better on a quiet network, but it can never beat physics. You only estimate one-way delay by assuming the path out and back are similar, which is often untrue. Precision time protocol pushes accuracy into the microsecond range on local nets by letting switches timestamp packets in hardware, cutting queuing error. High-end systems add dedicated timing links and disciplined oscillators that hold phase between syncs. Above that sits GPS and other satellite constellations broadcasting a steady, leap-second-free timescale. A receiver with a clear sky view can steer a local clock to nanoseconds, but even GPS has delay, multipath reflections, and occasional outages, and relativity corrections are baked into the satellites to keep them honest. All those are wall clocks, which aim to match civil time. Software also needs monotonic clocks that only move forward and ignore leap seconds so timers do not hiccup. Even with care, distributed programs still face the basic problem. You cannot reliably decide which of two far apart events was first if the messages announcing them arrive in different orders. The fix is to stop pretending and track causality directly. A Lamport clock assigns increasing numbers to events in a way that respects happens before. If A sends to B, then B's receive is later than A's send, but unrelated events can tie. Vector clocks give each participant its own counter and ship the whole vector, so the system can tell whether one event happened before another or whether they were concurrent. That mirrors physics. We can always order causally connected events, but space-like separated events have no absolute order. Big services blend these ideas with real clocks. Databases that must look consistent worldwide attach time intervals, not single timestamps, because network latency means the current time is uncertain by some window. If a transaction must appear global and ordered, the system waits out that uncertainty so before and after are meaningful everywhere. When teams cheat and use last write wins with naive timestamps, clocks skew bytes. A slower server's later write can be stamped earlier and get overwritten. So modern stores either synchronize well, tolerate conflicts and merge, or gate operations behind leases and locks tied to a single authority that hands out the present leap seconds cause practical mischief here too. Operating systems that jump the clock by 1 second can break assumptions like timestamps only increase. So large operators smear the extra second gradually over a day, trading legal exactness for stability. Others freeze the leap until midnight internal time and replay it in logs with care. Security piles on more constraints. Cryptographic signatures and certificates rely on time windows, so if an attacker skews a machine's clock, it might accept expired keys or reject valid ones. Good clients distrust lone time sources and cross-check with multiple signed feeds. The moral that falls out is the same as in space-time, but written in code. There is no perfectly shared now, only local clocks plus messages that move no faster than the medium allows. Strong systems treat time as a measured quantity with error bars. Respect happens before instead of fantasy simultaneity, and design around the fact that causality is the only global order you can trust. In other words, the internet runs not on a universal second hand, but on agreements, corrections, and humility in the face of latency, which is just a practical name for the speed of light and the mess of the real world. There's a quiet bridge between time and energy that explains a lot of everyday physics in one stroke. When the rules of a system don't change with time, when its equations would look the same yesterday, today, and tomorrow, then a single number stays put through the motion, and we call that number energy. This is Noether's theorem in plain clothes, a deep bookkeeping result that says every symmetry buys you a conservation law, and the symmetry, shift all events a little earlier or later and nothing changes, buys you energy conservation. You feel this whenever a pendulum swings in a vacuum and the sum of potential and kinetic energy is constant, or when a planet loops the sun and the total stays fixed because space around the orbit doesn't pull new tricks hour by hour. Break the time symmetry and the rule loosens. Push a child on a swing, external work, and the swing's energy grows because the setup now changes with time. Let friction act. Hidden little collisions with air and the pivot, and the swing's mechanical energy shrinks. But if you include the warmed air, the total still balances, which is the point. Open systems lose energy only because you drew your boundary too tight. Close the boundary and the ledger closes. In electronics, the same story runs. A driven circuit has a time-dependent source, so energy sloshes in and out through the terminals. In a laser-cooled atom trap, changing light fields siphon kinetic energy from atoms. In chemistry, if you shake or heat a beaker, the reaction pathways open because the rules now depend explicitly on your time-varying drive. Gravity folds a new twist into this. In Einstein's theory, energy momentum is locally conserved. The stress-energy flow has zero divergence, which means what leaves a tiny region enters its neighbor. But globally, the concept total energy of the universe only makes sense when space-time has a steady time symmetry. Technically, a time-like killing vector, so in a perfectly static star or around a non-changing black hole, you can define a clean conserved energy for each particle. However, the real cosmos is expanding, and that expansion means there is no single global time symmetry to anchor a single global energy. That's why photons from a distant galaxy reach us redder and less energetic than when they left, not because they spent energy crossing a field, but because the stage itself grew and there was no universal time translation symmetry to protect their energy. Locally, inside any lab, the books still balance exactly, but the entire universe does not owe you a total that never budges, which is why cosmologists warn that energy isn't globally conserved in an expanding universe, is more a statement about missing symmetry than sloppy accounting. This perspective cleans up common puzzles. A satellite's lost orbital energy during atmospheric drag is sitting as heat in the thin air. A damped oscillator's dying amplitude is energy poured into the surroundings. A microwave oven creates hot soup because you deliberately drive the system with a time-dependent field plugged into the wall. And the cosmic microwave background's photons cooling with time is the sensible result of evolving geometry, not a violation that needs a refund. It also sets a compass for new theories. If you claim a perpetual motion machine, you are smuggling in a time dependence you forgot to count. Some hidden battery, temperature gradient, or moving boundary. Because where there is exact time translation symmetry, there is exact energy conservation and no free lunch. If you claim energy is meaningless in gravity, you are smearing scales. Local conservation is razor sharp, but global conservation needs a global clock. The real universe does not have. The take-home is sharp enough to keep. Steady rules in time give you a conserved fuel. Changing the rules pumps or drains it. In curved, growing space-time, the rules themselves evolve, so only local ledgers close. And that is not a bug, but the reason your car runs, your phone charges, lasers cool atoms, and ancient starlight arrives, stretched by the breathing of the universe. It sounds backwards at first. In your kitchen, mixed means high entropy, and separated means low. Yet cosmology says the very smooth early universe had low entropy, and the clumpy universe of today, galaxies, clusters, black holes, has much higher entropy. The fix is that gravity rewrites what typical looks like, because a nearly uniform cloud under its own pull is an unlikely, finely tuned state, while a cloud that has broken into dense pockets and empty voids is the generic endpoint. And along the way, gravity turns potential energy into heat, radiation, and, at the extreme, black holes, which are entropy monsters. A single stellar mass black hole carries more entropy than all the ordinary matter that formed it, and a supermassive one in a galaxy's center dwarfs the entropy of the galaxy's stars and gas, with the rule of thumb that a black hole's entropy scales with the area of its horizon, not the volume inside. So clumping plus collapse ramps the universe's entropy up fast. Now rewind to the start we infer from light. The cosmic microwave background shows the young universe was astonishingly smooth, with temperature variations of about 1 part in 100,000, which means gravity had not yet done its separating work. Those tiny ripples acted as seeds. Slightly over-dense regions grew. Slightly underdense regions emptied, and over billions of years the cosmic web of filaments and voids emerged. Stars lit, some died and left black holes, and mergers stacked black holes into giants, all of which drove entropy upward. So why call the smooth state special in the first place? Because in a gravity-free gas, the maximum entropy is indeed uniformly mixed, but with gravity, the maximum entropy at fixed mass and volume is a configuration dominated by collapsed objects and diffuse radiation, and the smooth case is a kind of poised domino line that has not yet fallen. Roger Penrose sharpened this into a geometric guess, the Weyl curvature hypothesis, arguing that the early universe's free gravitational field, its tidal shape-twisting part, was near zero, which is another way to say gravitational entropy was tiny, leaving room for it to grow as structures formed. Tiny here is not rhetoric. Compare the entropy in the early cosmic plasma to the entropy that would be carried by black holes made from the same matter, and you find an absurd gulf, meaning there was a huge entropy budget left to spend, and the spending is the arrow you live by. Where does inflation fit? The early burst of accelerated expansion that flattens and smooths space and stretches quantum jitters into the seeds we see in the microwave background. In the standard story, inflation neatly explains why the early universe was so uniform and why those ripples had just the right statistical pattern. Penrose counters that making a special inflating patch may itself require low entropy conditions, so smoothing cannot create low entropy from nothing. The debate is live research, but whichever side you favor, the observational pillars stand. The background glow is smooth, with tiny scale-structured ripples. Those ripples grew under gravity into the web we map. Black holes formed and hold most of today's known entropy, and the sum of mixing, collapsing, heating, shining, and swallowing gives the universe a clear thermodynamic slope. That slope ties the cosmic arrow to the everyday one. Your coffee cools because heat spreads, but the free energy that made coffee possible came from stars that burned because gravity made clouds fall, heat and fuse. And those stars, in turn, are part of a larger cascade that, barring surprises, runs toward a future where most mass is locked in black holes and thin radiation, and on even longer scales the holes slowly leak away as Hawking radiation, leaving a cold, dilute bath that is as close to done as physics can say. None of this needs a new time law. Give gravity a low entropy start, and it builds the landscapes that make arrows obvious. Records in rocks and light, flows of heat, living gradients to run brains. And that is why smooth then clumpy is the simple backbone behind both the red glow in the sky and the one-way feel in your day. In everyday life and in most of physics, events line up in a crisp order. First you flip the switch, then the lamp glows. First the cue strikes, then the ball rolls. Relativity already softened that picture at long distances by saying there is no single global now. Yet it kept a hard rule locally. If A can influence B, A must sit in B's past light cone, and everyone agrees on that order. Quantum experiments add a stranger twist, not by letting effects outrun causes, but by making the order itself part of the game. The clean example is the quantum switch. Think of two operations, A and B, say two tiny filters that change a photon state in different ways. Classically, you choose an order, A, then B, or B, then A, and the outcomes differ because the two operations do not commute, just like putting on socks, then shoes versus shoes then socks. In a quantum switch, you entangle the control, which chooses the route, with the target, the photon being processed, so that the photon explores A to B and B to A at the same time in a controlled superposition. Only when you measure the control do you resolve which order happened. Before that, the combined device behaves as if the world had no fixed sequence for those two steps. This is called indefinite causal order, and it has been demonstrated with interferometers that route single photons along two paths whose histories recombine, and with other platforms that mimic the same logic. What changes when you allow order to be fuzzy is not causality. No one sends a message to yesterday, but the power of certain tasks. Some communications problems, sensing tasks, and query schemes can be done with fewer resources if you are allowed to run operations in a superposition of orders. It is like phoning two offices that each forward you to the other. Classically, you would waste time bouncing around, while the quantum switch lets you try both orders at once and interfere the results to dig out an answer more efficiently. The rules remain tight. Even in these setups, signals never outrun light, and you cannot create grandfather paradox loops. The indefinite order lives inside a sealed quantum circuit. Once you open it and extract a classical record, you get definite outcomes that respect ordinary cause and effect in your lab. Why should this be possible at all? Because quantum theory treats what happened as a pattern of correlations between systems, and until you burn those correlations into a classical record, some features, like which route was used first, can remain unresolved without contradiction. The idea may reach deeper. Gravity ties time and space to mass and energy, and many suspect that at very high energies, or over very small spans, the causal structure of space-time itself could fluctuate. In such a world, it would not even make sense to say Event A happened before event B in the sharp global way we like. Only local, relational statements would survive. Early proposals model this with process matrices that describe correlations without assuming a fixed background order, yet they still enforce the basic no-signaling constraints that keep paradox at bay. If a full quantum gravity theory confirms that causal order can be genuinely indefinite in nature, the lesson will not be time is fake, but before-after is a context-dependent property that emerges when systems are large, signals are recorded, and geometry is smooth. Tie this back to your daily arrow, and the message is modest and clear. Your coffee cools because of statistics, not because the universe writes future on each second, and your GPS works because proper time along satellite paths is well defined in a smooth space-time. Quantum switches do not alter that. They show that when you zoom in and keep records soft, you can let two small processes borrow the same slot in sequence and still tell a consistent story at the end. Cause and effect remains local and lawful. Order can be quantum while it lasts. And time, once you average over enough degrees of freedom to make a stable record, snaps back into the familiar sequences that run your day. We can now say something plain without poetry or hand-waving. Time is not a single thing you can hold up to the light. It is a stack of realities that fit together. As a physical coordinate, it is as real as distance, but local and flexible. Your proper time is what your own clock reads along your path, and motion and gravity stretch or squeeze that reading with a precision your phone already depends on. There is no global now to nail across the sky. Simultaneity far away depends on how you move, and cosmic time is a helpful average for an expanding universe, not a sacred present. The direction you live by is not a magic law baked into the equations. It is the typical outcome of statistics given a special beginning. The early universe was astonishingly smooth, low gravitational entropy, so there was room for structure to form and for countless processes to run downhill. That downhill roll lines up every arrow that matters. Heat spreads, radiation flows outward, quantum superpositions decohere into stable facts, memories accumulate, records persist, and engines work. Your felt flow, minutes stretching or vanishing, lives in biology and psychology. The brain stitches a short window of signals into a smooth now, speeds its internal ticker when aroused, writes denser memories for novelty, and compresses routine. That construction does not make physics subjective. It explains why the same wall clock can govern a lab, while your experience of those seconds bends with attention, mood, and sleep. Quantum theory adds honesty rather than mystique. In the textbook, time is a parameter, not an operator, and good clocks are quantum devices that compare phases. At larger scales, entanglement with the environment makes definite records and gives the measurement arrow its direction without breaking causality. The exotic corners matter but do not rescue paradox. Closed, time-like curves on paper demand impossible matter or explode under quantum back reaction. Indefinite order inside a quantum circuit boosts some tasks, but never lets you message the past. Black holes slow clocks to a crawl for distant watchers, yet infallers feel normal proper time, and the best evidence says information is scrambled, not destroyed. The deepest layer may be relational or discrete. Page-Wooter's clocks, causal sets, loops, holographic hints that geometry rides on entanglement. But whatever replaces our current maps must reduce to smooth space-time where we can test it, and there, time behaves like the ruler our instruments already trust. Agency survives the block metaphor because causation is local. Within your light cone, different choices produce different downstream histories, and in a probabilistic world, could have done otherwise, is not a slogan but a statement about different outcome distributions under different interventions. Outside the lab, Our shared second is engineered, not absolute. UTC is cesium ticks plus politics. GPS is steady time plus relativity corrections. Data centers stop pretending there is a perfect shared present and track happens before with error bars. Fold everything together and the picture is sturdy. Time is the bookkeeping of change with three faces: a geometric face that sets the fence posts of cause, a statistical face that supplies the slope from low to high entropy, and a cognitive face that turns delays into a usable stream. None cancels the others. They interlock. If you want one last sentence to carry, time is real enough to bend under mountains and to steer satellites, emergent enough to arise from correlations and coarse graining, and human enough to feel elastic when your brain edits the world. Three truths. One world, no magic needed. Thank you so much for listening. Good night.